Welcome everybody. Before we really get started with our course, A Friendly Introduction to Abstract Algebra, let me tell you a bit about what algebra actually is. We can divide it in two categories, classical algebra and modern or abstract algebra. First of all, where does this word come from? A Persian mathematician who taught in Baghdad, Al-Khwarizmi, coined the term algebra, which means roughly reunion, in the sense of reuniting broken pieces or putting broken pieces together. What he meant by that is, I assume, like for example, if you try to solve this equation, the 4x here and the 2x here are divided, are broken, so you have to put them together, like bring this 2x here and bring the 2 to the other side, and then you can solve. I think this is what he meant by algebra or reunion, and the Latinized version of his name is algorithmi, so this is actually where the term algorithm comes from, to honor one of the founding fathers of algebra. Okay, and now what we call classical algebra is mainly concerned with solving equations, usually with one variable or unknown, what you know from school, like linear equations ax plus b equals 0, or any equation that can be brought to this form, and then quadratic equations ax squared plus bx plus c equals 0. And of course, you have all learned the quadratic formula in high school. And these here, especially the quadratic equations, have a very, very long history. Of course, this list here is not meant to be exhaustive and probably in some places wrong. I'm no mathematical historian or anything like that. But just to give you a rough overview, in the old Egyptians, about 2000 years before Christ, actually had methods to solve these kinds of equations. In those times they didn't have this notation or even the x, but it was what we call rhetorical algebra. All the problems were posed using words and sentences, and so were the solutions. So they did not have the classical quadratic formula as we know it, but they were able to formulate problems that led to these kinds of equations as we write them down today, and they were able to solve them. The same in Greece, of course, the famous Euclid, 300 before Common Era. Also, I think mostly rhetorical methods. Diophantus, 250 Common Era, I think had a more algebraic approach than in old books or scripts from China. In this time here, you can find writings about quadratic equations and their solutions. In India, around this time, there was a famous mathematician named Brahmagupta. And then Al-Khwarizmi, we have met him before. I think he was one of the first guys to have actually an algebraic method to solve these equations. Then Simon Stevin, Flemish mathematician, Belgium, 1594. We have written proof that he actually was in possession of the algebraic formula that we know today. The same here, François Viète in France, or Vieta in Latin, about the same time. He is considered to be one of the first Europeans that introduced calculating formally with x and doing symbolic algebra. Then, of course, René Descartes in France, a little bit later in his book on analytic geometry, has a formula for solving these equations. So this is just to show you that these equations here and their solutions have a very, very long history. Then, after quadratic equations, there are cubic and quartic equations of this form: ax to the third plus bx squared plus cx plus d equals 0, and the same with the starting term x to the fourth power. And here we have some famous names from the Italian Renaissance, of the middle of the 16th century. first and foremost Girolamo Cardano, who published a very famous book, Ars Magna, The Great Art, in which there are solution formulas, the famous Cardano formulas for solving these equations. What is a bit confusing to me is this date here compared to those, because if he could solve those equations at this time, then surely he must have known the quadratic formula. But again, I am no math historian, and it's actually very recommendable to read up on the life stories of those guys, and especially Cardano and Tartaglia, who was kind of his opponent. I won't go into any details here. Pinter, for example, is a good reference, or just look it up on the internet. Very, very dramatic life stories of those guys. And back in the day, people did not publish their results usually, but kept them on their own because they actually made money by doing competitions and solving equations. And after a long time of persuasion, Tartaglia told Cardano about his findings about these equations, and he had to promise him not to publish this, but he did it anyway. So those two actually became enemies for the rest of their lives. Then also Del Ferro and Ferrari, which was a student of Cardano, must be mentioned. So those Italian Renaissance mathematicians solved the cases of cubic and quartic equations. And then after that, of course, a lot of mathematicians tried to find a formula for the quintic equation. And a lot of great minds tried to do that, but they had no success. For over 200 years, no one was able to find a solution formula like for those equations containing square roots, third roots, plus, minus, divided by, etc. Nobody could do it. And then it gets really interesting. A young Norwegian prodigy by the name of Niels Henrik Abel, also read up on his life story, very sad, he died much too young. He proved in 1824 that there actually is no formula for quintic or even higher equations. Later on, when we talk about fields and Galois theory, we will make more precise what we mean by formula exactly, but that's not the point here. He really proved using methods that weren't known before, what we now call group theory, that it is impossible to find a solution formula for this equation here. This was a big surprise and also a shock to those mathematicians who tried that. And at about the same time in France, in 1832, a youthful prodigy named Évariste Galois played around with roots of polynomials and discovered or created what we nowadays call a group of permutations. And those two were two of the founding fathers of what is now called modern or abstract algebra. You can see here the term modern is a bit of a misnomer because that's not so modern anymore, but still the term stuck. So I think it's better to use abstract algebra. I would also recommend that you read up on Galois and his life story. He was actually shot to death in a duel at the young age of 20. And in the night before the duel, he wrote down all his findings and gave them to a friend, and he published them later on. So what is abstract algebra? Whereas here we are concerned with solving equations, this is something very different. Modern or abstract algebra is studying algebraic structures. What does that mean? An algebraic structure is, loosely speaking, a set of elements together with an operation that combines two of those elements to give you a new element of this set. The easiest algebraic structure that we are going to start with is the structure of a group. There you have a set and one operation to combine two elements of this set to give you a new element. And of course, this operation must satisfy certain rules. Then another example of an algebraic structure is a ring. There you have a set R together with an addition and a multiplication, so two operations that again give you an element of this set, and also they must satisfy certain rules or axioms. And then even more special, or a special case of a ring is a so-called field. There you have more conditions. You have the same operations, addition and multiplication, but you have more axioms that need to be fulfilled. Another example of an algebraic structure is the structure of a vector space. There you have a set with an addition, and also you have a field and what is called a scalar multiplication. Now you not only combine two elements of your set with addition, but you can combine an element of this set, a vector, with an element of this field to give you again an element of this set V here. So the operation we are talking about need not be between two elements of the same set, but can also be mixed, as you see here. Then a generalization of a vector space is the notion of a module. It's the same idea as here, but instead of a field, you have a ring. So your scalars are not from a field, but from a ring. Otherwise, the axioms are the same. So vector spaces are a special case of modules. Then there are also algebraic structures that are called algebras. An algebra is a vector space together with a multiplication. So you can multiply not only scalars with vectors, but two elements of your vector space. So even more structure than a vector space. This can also be generalized to algebras over a ring. I'm not going to discuss this here. Another interesting algebraic structure is that of a so-called Lie algebra. This here is a G, this small fractal, I don't know the English term. This small G here is a vector space with a bilinear operation that is no longer associative, the so-called Lie bracket. So all these operations here satisfy some kind of associativity. This here no longer. And the list goes on. What I left out are, for example, lattices and Boolean algebras, but we are not going to be concerned with those objects at all, so I left them out. So, and of course, I can't give you all the formal definitions now because this is just an overview, but just that you get the idea. So, classical algebra is about solving equation using addition, subtraction, multiplication, division, square roots, higher roots, and so on to find solutions of these equations. And in modern or abstract algebra, we study structures, algebraic structures. Now you might think, well, there's no connection at all, but there really is. And actually Abel and Galois used this stuff to answer questions that came up here. For example, why can't we find a solution formula to this equation? Abel answered that using group theory. Can't go into any details here, but using group theory, he showed it is impossible to find such a formula because a corresponding group has a certain property and those two do not fit together. And now mathematicians are satisfied just studying those objects for their own sake, and this is actually already pretty interesting, but there are actually very, very fruitful applications of these things here in such fantastic disciplines as algebraic number theory. For example, in the proof of Fermat's last theorem, Andrew Wiles used a lot of algebra and came up with new concepts himself. Then there is algebraic topology, where we have, for example, the homology and cohomology groups or homotopy groups or whatever. And then, of course, there's algebraic geometry, in which we have even more fantastic objects like sheaves and schemes and whatever. And besides the applications in pure mathematics, there are also real-life applications of this knowledge of algebraic structures. For example, in cryptography, group theory, for example, is a very important tool. Even in computer science, like in coding theory or graphics or whatever, this is used. Then in financial math, and of course in physics, in particular, especially in particle physics, a lot of this stuff is very, very useful. All right, what we are doing here is an introductory course. Of course, we cannot go into any details here, but we will start with a thorough studying of groups, rings and fields, maybe a bit modules, I'm not sure yet. And then we see where we want to go. Right now I can't exactly tell how far we will go. I think covering this here in depth will take well over a year of weekly videos, and I'm not sure at all if I can uphold doing that for such a long time. So let's get started with groups and see where all this takes us. I'm very excited. If you're excited too and looking forward to the videos, please support this channel and subscribe, like, share this video and help this channel to grow. I would really, really appreciate that. All right, in the next video, we are going to get started with part 1, namely, I will give you an introduction to the concept of a group. Hope to see you there, and bye-bye.